So obviously we're going to talk about MassWorks as it's applied to the Agilent GC-MSD. And just to remind you, what does it do? What it does really for GC-MSD data, it adds the ability to do unknown formula ID. And it does this through a mechanism of improving the accurate mass of the instrument. So normally for a typical MSD, the mass accuracy spec is typically on the order of a few tenths of a Dalton. With our calibration technology, we can improve that down to about the third decimal place, so about a factor of 100. That helps. It's not TOF type mass accuracy, but it's getting into the realm where you can start to get a reasonable list of formulas for formula candidates for possible ID. The other thing that we throw into the equation is something which I'll talk a little bit about. And again, if you have questions, please let me know. Called spectral accuracy, and that really combined with, and we'll talk about what that is. That combined with mass accuracy enables really good formula identification on a single quad instrument. And in particular, the Agilent instrument is extremely high performance. So we tend to get the best results on that type of instrument. There's some other things. We probably won't go into it today, maybe a little bit, but because of this calibration technology, even if you have overlapping ions, we can actually still do very accurate analysis. And we have a lot of users also that are interested in looking at isotopes, which tend to have overlapping ion fragments. And we can actually unravel the relative quantity of those isotopes, but we probably won't get into that today. And by the way, this specification here, accurate mass, this is of 0.005 m over z, and spectral accuracy is a published spec by Agilent using an injection of 1 microliter of OFN at about 272 Dalton. This is not a new technology. It's been around for over a dozen years now, and it's well proven and highly published. We literally have thousands of users throughout the world using it. And in fact, it's if you're an organic chemist and you want to publish a new structure, one of the things you need is to have a confirmation of the formula. Generally, they look for accurate mass measurements. Our effective mass accuracy using the combined metrics of accurate mass and spectral accuracy are actually accepted for publication by all of the major organic chemistry journals. So again, it's just emphasized it's not magic, it's not new, it's well established and well used technology. I'm not going to go, I'm going to kind of skip through this pretty quickly. But there is a couple of important points. This is really a kind of a description of how our technique works for providing accurate mass and high spectral accuracy on a quadrupole. So if you do want me to slow down, please say something. Otherwise, I'm going to kind of go through this pretty quickly. And basically, the idea is that in mass spectrometry, you typically are looking at centroided data from a low resolution instrument such as a single quad. But in reality, what the instrument is measuring is a continuum, also called profile mode data or raw mode data. And what the vendors will do is they'll take that raw mode data and they'll find the peak locations for each of those. And this is looking at a single isotope. And so you see the isotope patterns. It's fairly high mass, so you see a nice set of isotope patterns where you have the monoisotopic peak there, largest peak. You have the A+1 and A+2, and you can even see a little bit of the A+3 there. And that gets transformed in the vendor software to give us this centroided data. Um, so the interesting thing about mass spec, of course, as we all know, is that when we have an accurate mass machine, we can use that to help identify a formula because every single unique formula in the world has a unique mass, although sometimes obviously those differences are quite small. But the other piece of information that's a little bit underutilized, in fact, I would say a lot underutilized, is that we also know the isotope distributions in nature. So even if compounds have very similar mass positions, they can have very unique isotope patterns, and this is kind of the fundamental thing that we're going to metric that we're going to use, which we'll call spectral accuracy, and we'll talk about that. So this is actually a real measured mass spec in profile mode, and you can see that the line shape is kind of distorted. That's pretty typical in mass spec, and it's really dependent upon what they call the tune of the instrument. And the interesting thing is mass spec is really the only analytical measurement tool where we can very accurately and very rapidly calculate any spectrum of any given formula based on first principles, because we know obviously the masses and we know the isotope distribution. If you look at other spectroscopic techniques in using electromagnetic radiation to make measurements, whether it's in the infrared, X-ray, or whatever, the line shapes are actually very well known because they're defined by the physics of the optics in the instrument, which is very good and very reproducible. That means that we can measure effectively the shape or the curve of a sample between two different instruments and even two different vendors' instruments, as long as they're at the same resolution. And we can get very accurate matches. If we try to do the same thing with mass spec, we can't do that because the line shape is really unknown. It's undefined. It's really a function of the tune. And that's a shame because if we did know what the physics of the underlying line shape was, we could use that to more accurately model these isotope profiles. And that's the thing that we call spectral accuracy. So in general, when the vendor does a tune, they will tune for the line shape a bit, but the main thing they're doing is they're simply adjusting the x-axis so that the mass position lines up with the calibration standard. In our approach, what we do is this is a measured line shape again in profile mode, and that is very important. We need to have the data acquired in profile mode, and we'll talk about that, how to do that at the end of this. But what we do here is we take that measured line shape and we actually choose a preferred line shape, which is actually an analytical function like a Gaussian. And we want to calibrate this mass spectrum not only to the mass position in the x-axis, but we also want to calibrate this line shape pattern to a known analytical function. That would allow us to much more easily model these isotope patterns to give us more information. So this is actually what you see here, looks like centroided data. This is actually a theoretical spectrum of a mass spectrum of our standard, which we can calculate very precisely. You can see all the isobars here. This is infinite resolution. And we know we've chosen a line shape here, which we're going to calibrate with. And if we simply convolve that line shape, we get a theoretical, or actually what we call the true spectrum, what we would like the mass spec ion pattern to look like as that profile mode spectrum. And then what we can do is we can simply look at the difference between the measured line shape and this very nice calibrated line shape spectrum, and we can actually through a little bit of matrix algebra, calculate a correction function, which when applied to an unknown ion, calibrates it not only to the X position, okay, so you can see the shift there, but it also calibrates the line shape to this well-defined mathematical function. And that allows us to model the isotope patterns very, very accurately. And that's what we call spectral accuracy. So that's how, really very simply, how the calibration works. So what does that give us? Well, if you think about it, um, when a vendor does the centroiding of the data, he's working off this raw data here, this black line here. And so how do you determine where the position of the peak is? Well, you might look at the maximum, or you might look at a few peaks across the top, and you might place the centroid there. Um, the that's because of the relative low resolution of the instrument, the actual mass accuracy that you obtain from that approach is on the order of a few tenths of a Dalton. However, since we've calibrated this spectrum to a known line shape, so we know what the underlying line shape function is of this first of the monoisotopic peak here, when we do the centroiding, we can actually fit all of the points through the profile spectrum. So we're taking advantage of an averaging effect because we can actually fit the entire isotope profile. That improves our mass accuracy dramatically from about a few tenths of a Dalton all the way down to about the third decimal place, or about 100 times better mass accuracy. Now, as I said, that still doesn't get you to the point where it's very easy to do formula identification, because you have to use this 5 millidalton window to look for all the potential formulas for an unknown, and so you still get a pretty long list. But what we can do is we can take advantage of this now well-calibrated isotope profile, and we can fit it against those list of formulas to find out which isotope pattern matches best. And this is called spectral accuracy. So really, we're using another dimension of the mass spectrum besides just accurate mass to basically improve our formula ID. And it is actually a very powerful tool. And in some cases, it's even more powerful than mass accuracy. So that's our secret sauce, and in a nutshell. So let's dive into the acquisition requirements. Now, when we looked at that data, you saw that we were always working in profile mode, and you're probably used to primarily working in centroid mode. What it means is you're going to have to acquire the data that you're going to do accurate mass formula identification on in profile mode. So how do you do that? Well, there's a number of rules that you have to follow. And here's kind of a list of them. The first one is obviously and I'm going to show you how to set this. The first one is the instrument must be set to acquire raw scan data. Also, depending on who you talk to and what the vendor is, it's also known as profile mode data. The instrument threshold counts, the filtering or the zeroing of a lot of instrument vendors will apply a filter so that any signals that are below a certain threshold are automatically zeroed. It makes the spectra look better, especially when you're looking at it in centroid mode. But that information is actually, there's noise in that information, and that noise is actually very useful. We utilize that noise in our calibration to effectively make it all work. So we need to set that to as small a value as possible, preferably zero. Okay, so we need to set the threshold counts in the instrument to zero. You would like to set the instrument scan rate to be reasonably fast. Obviously, for Agilent, we tell people that we'd like them to set the sampling rate to a factor of what they call 3 or 2. You don't want to go at the fastest rate, but those rates seem to work best for most data. Um, it's if you're only measuring compounds in a small mass range, there's no need, unless there's an experimental need, to scan a very large mass range. The shorter you can scan the mass range, the more scans you're going to get, and the better the signal to noise that you're going to get, and the better results that you're going to get. And this is true of any kind of measurement that you're doing in the GCMS. And then finally, we need our calibration standard. So we need to know, we need to have a set of ions across the mass range of the GCMS to do our calibration. We need to know the formulas for each of those ions because we're going to perform our little magic calibration on them. And the nice thing about GCMS is there's a very nice built-in calibration standard, which is the calibration gas built into the instrument, which is PFTBA, which is a fluorinated compound. And so the idea is that you do the GCMS run, and then at the end of the run, you can after the oven cools down, and we'll look at that. You just need to turn on for about 30 seconds or less the calibration gas, and that's used as the calibration standard. And in fact, with the Agilent system, if you do this in a run, we'll automatically find that calibration gas and will automatically do the calibration for you. So in effect, you don't have to do anything. It just open up the file, it calibrates itself, and all of a sudden you have accurate mass data. You can, most people will turn on for runs that they want to do this formula identification on. They'll run it under these conditions. They'll turn on the PFTBA gas at the end of the run. You don't have to do it for within the run. You can also just collect a single calibration run, for example, at the beginning of the day, and apply that to spectra that are acquired throughout the day, as long as you don't change the acquisition parameters of the mass spectrometer. And so we always recommend to people that if you're going to do it this way, you need to acquire the calibration about once a day. In fact, because the Agilent system has a thermostated quadrupole, this makes it extremely stable. So in fact, we've seen independent measurements done to look at this stability, and in fact, the calibrations are stable, could be stable over many days. But we like to do it, at least tell people, at least once a day. So how do you set it up? I don't know if you're using ChemStation or you're using Mass Hunter, or what software you're using on the instrument. That's a question.
ChemStation and
Okay.
Mass Hunter, both.
Okay, I'll show you both. That's no problem. So, and I'll send you this. I mean, we have documentation too that probably you should have gotten pointed to, but I can send you this slide presentation as well. It's
Okay,
a nice little summary. After we're done, I'll make a PDF and send it out to you. So in the ChemStation, it's basically in the acquisition mode, you set it to raw scan mode. That's your profile mode. Agilent calls it raw scan, which is fine. The thresholding we talked about is should be set to 0, so that's set here. And the sampling rate, which is the scan, really is scan speed, and Agilent uses these values that I think go from 1 through, I forget how the highest number is, but the smaller the number, the faster the scan rate. We recommend to people that they set the scan rate to 2 or 3. Obviously, you want to take into account the chromatography to make sure you get enough scans over the peak width, depending on what kind of chromatography and column that you're using and what its effective resolution is. And then, and then finally, what you want to do is you want to set up a timed event in your method that turns on the calibration valve at the end of the run. And you want to do this after the oven cools down. And that's set up in the timed events table here. And you just set up a time to turn the valve on and to turn the valve off. Here it's set to go on for about a minute, but in actuality, 30 seconds or less is fine. And Mass Hunter, it's actually a little easier. It's all kind of on one page here. The acquisition type, you'll notice that the language was changed from ChemStation as raw scan, and in Mass Hunter, they call it profile mode. Okay. Again, your threshold should be set to 0. Your scan speed here, they give you the equation, but the n equals 2 or n equals 3, that's the same value. That's the equivalent value that you use in the chem station. And then very importantly, this is just turning on and off the calibration gas at the end of the run. So again, I'll send you these slides, and you can take a look at them. And I think it's a good guide, simple guideline to use for acquisition. And just to give you an idea of what it looks like in chromatogram space, I just arbitrarily made a temperature ramp here. I don't actually know what the temperature ramp was, but just to show you fundamentally how it works is here your oven temperature, you set your ramps up here, you go through your run. At the end of the run, you cool the oven down, and that takes some time, so you set the cool down rate. And then when the oven is cooled down, you want to turn on the calibration gas. So this little peak right here, that's actually the calibration gas being injected into the instrument. And when you open up the data file in MassWorks, it will automatically find this calibration gas for you, and it will automatically create and apply the calibration to the data. And we'll look at that when we look at the product. Okay. Let's see. I'm going to skip this for now, and let's just move on. Do you have any questions before I move on to looking at MassWorks itself?
Not yet.
Okay. So this is MassWorks. I've already started it up. It's actually, as you'll see, it's actually very easy to work with the Agilent data and do the calibration and mass accuracy on this. There's actually two modes of operation. There's what we call the analysis mode, and the analysis mode is where you look at the chromatogram and you would average some spectra across a chromatographic peak, and then you might go in and look at the spectrum. You can use now the calibrated accurate mass data to do unknown formula ID, and we'll see how that works in a minute. The calibration mode is actually where you build the calibration. For the Agilent, you really will probably never use this mode because it's done automatically for you as long as you turn on that calibration gas. For other types of instruments, for example, like LCMS, it's a little more involved to develop a calibration, and the calibration there's no like one standard calibration or LCMS. So you would actually go in here and you might actually build a calibration. And I'm going to skip this for now. We can go back at the end if you're interested, how you would build one manually, because like I said, you probably will never use this. So how do you calibrate a Agilent file? Well, what you do is you're in analysis mode, and then you're going to open up the mass spec data from the Agilent system. So you say open MS data. Now, let me explain here. The Agilent, and for historical regions, all the data from the run is closed in a single folder. So in the Agilent software, you would simply click on the folder and it will open up the underlying data. That's kind of special to Agilent. So something a little bit different, if you want to open up the actual mass spec run in the data in MassWorks, you actually go to the .d folder, you double click on it, and you'll see a file that's created called .ms. That's actually the ChemStation format binary file. You just need to point the software to that and say open, and that will actually open the run data from the run. So that's a little bit different from what you're used to. Um, if you're using Mass Hunter actually acquires the data in a different format, uh, which is the Mass Hunter format. But conveniently, because so many people go back and forth between uh, Mass Hunter and ChemStation, they also always create uh, a ChemStation file. So even if you've collected the data in Mass Hunter, you'll still see this .ms file, which is the ChemStation format. Okay? You can also open up the uh, Mass Hunter data file, which actually is in a file called msprofile.bin, but it's not necessary. Just this is always going to exist. Just open it up. So you say open it, and when you open it, now I previously already opened this file. You saw that little dialog box pop up, and what it said is it said uh, this run already has a calibration file created for it, and it's going to use that calibration file and it's going to apply it to the run, and then now all the mass spec data is going to be accurate mass. If you hadn't opened the file before, when you first open it, the software will automatically go and look for that PFTBA calibration gas at the end of the run. It will then automatically create a calibration file from that and apply it. So it just sits there and a little dialog pops up and it says creating a calibration. I could probably show it to you for a different run. So let's see. It will look something like this. Uh, that's a pesticide run, for example. So there, it didn't have the calibration gas, so it's warning me. But if it did have a calibration gas, it would just automatically create it. So let's jump to back to our cal. This is just a very simple run of the OFN that's used as a kind of a benchmark for the instrument. When you get the instrument, the installation engineer will probably inject this and this make sure that the instrument's within spec. So it's a very simple compound, fluorinated compound that gives a nice fragment pattern. So what you can see here is that's the OFN 1 microliter injection, eluting here at about 3.25 or so minutes. And then at the end of the run, you see the calibration gas was turned on. This was turned on much longer than you needed. This was actually something that was done a very long time ago. Generally, you only need about 30 seconds of the gas. So in MassWorks, it operates similarly in terms of the user interface to ChemStation or Mass Hunter. There are some differences, and let me just walk you through those quickly. If you want to zoom, and again, if you go to help, it's got an online help, and it has all the shortcuts for how you zoom and how you would navigate spectra, and it's pretty intuitive once you get used to it. Anyway, this is all included in that help file there. So I'll walk you through a few of the basics here. If you want to zoom in on a peak, I think this is very similar. You hold down the left mouse button, you draw a box around the area you zoom, and bam, it zooms in on it. So that's simple navigation. If you want to, there are toolbar buttons. So for example, this will reset it to the full scale. There's some other ones up here as well. I actually never use them, and I'll show you why. It's very intuitive how you zoom around and navigate spectra. If I zoom on that, for example, if I want to simply uh, scroll the peak or scroll to the next peak and look at another one, you simply grab the x-axis and drag it, and that gives you your scrolling in the x. Likewise, if you grab the y-axis, that'll scroll in the y. If you want to auto scale it on the y, you simply double click on the y-axis and it auto scales. If you want to auto scale on the X, you simply double click it and it auto scales on the X. If I've zoomed in and I want to just reset the scale, I can just double click on the intersection of the X and Y axis and it auto scales both the X and the Y axis. That's that's really simple, okay? So that's how you navigate. So let's take a look at this OFN and let's do a accurate mass analysis on this particular peak. So I'm going to zoom in on it, and if I click on it, anywhere I click on the chromatogram, you'll see the corresponding spectra showed up. Again, same zoom controls here. I just can zoom just like I did on the chromatogram, exactly the same tools. Um, and if I click, you'll see the spectrum. It's for the best results. It's always better to average spectra across the entire peak versus just simply looking at a single scan. The reason for that is, of course, when you average, you get better signal to noise. And because you get better signal to noise, you're going to get better results for pretty much everything. The way that you average is you can simply right click on the chromatogram and you'll see one of the choices here is mark an RT window. So that allows you to mark the boundaries to average across the peak. And so you click that and you click once, that's one edge of the peak, and then you click second time. And what it does is it creates this, shows this banded area here. And the spectra that we're now looking at down here is the average of scans across that peak. And that's the ideal situation. That's really, this is the spectrum that you want to work on. You can simply drag those. If you want to change those edges, you can grab them. You can change the averaging that way. There's also shortcuts to do the averaging, which make it really quick to do. If I hold the shift key down and I drag, it'll create a averaging section. Obviously, I'm just averaging pretty much noise there. I can select multiple peaks that way. I can go back and select the one I want to analyze. And so what we have here, so let's shift our focus now to the actual spectral data here. So this is OFN. We know what it is. So it's not like we're working on an unknown, but the fundamental principles are the same. So this happens to be the molecular ion peak. And so the idea is, of course, is if we have an unknown sample or we have a sample that we've run, maybe we're trying to identify, maybe we've performed the NIST library search on it, but we're not quite sure if it's the right match, or maybe the compound is unique in that it's not in the NIST library, and we're trying to figure out what it is, in which case we would like to go and look at the molecular ion if we can figure out where that is. Obviously, not all compounds have a molecular ion, but we can also analyze the fragment ions to look at the fragmentation. And obviously, that information is very powerful and can give us insight into the identification of the unknown compound versus just the formula. Because remember, in mass spectrometry, the accurate mass of an ion only gives us a formula. It doesn't give us a structure. It doesn't distinguish between isotopes. It only gives us a formula. But that's obviously a very important starting point for any unknown identification process. So this is your little isotope pattern. So remember now I'm looking in profile mode. That's the calibrated data. If you're interested, you see these little tabs over here. This really allows you to access all the functions for doing searching and for controlling what you see. For example, I can tell it to, I'm telling it here to show, if I want it to, I can actually create extracted ion chromatograms. That's sometimes useful, but in general, not the main principle for using this software. I can say show the peak labels on the total ion chromatogram, for example. I can say show the calibrated spectrum. I can also say this is the raw spectrum. So that's the raw spectrum. That's the uncalibrated data. and that's the calibrated data. And you can see the difference between the two. I can also look at both of them. So you can see a couple of things here. You can see that in the calibrated data, uh, it, it's the line shape is very well defined because we've calibrated to a known line shape. The raw data does not have a calibrated line shape, so that's typical looking of a well-tuned mass spectrometer, nothing unusual. You'll typically notice that the line width of the calibrated data is slightly wider. So it's slightly lower effective resolution, and this is done for mathematical reasons. The area underneath this curve is still exactly the same. That's preserved, but the peak is a little bit wider, so the intensity is going to be less. But the most important thing, though, is the ion count under those two curves is identical. Okay. Um, but in general, we're going to be working, and you can also look at the centroided data as well. We'll show you the centroid data if you're interested in that. But in general, we like to work in profile mode, and we like to work with the calibrated data. So this default view is what we're going to be working at. Now, the difference is when we look at this peak centroid here for the monoisotopic peak here of the molecular ion, as opposed to the mass accuracy being only good to that first decimal place. Now it's good all the way down to the third decimal place. So what that enables us to do is it enables us to do formula ID in exactly the same way that you would do it on a high resolution instrument. So one thing that you should think about, mass accuracy and resolution are two different things. You can have low resolution and still have accurate mass. You don't need to have accurate mass. Excuse me, you don't need to have high resolution to get accurate mass. That's why, even though this line, obviously it's a lot easier to do, and you can always do a better job if you have higher resolution, but we can do quite an admirable job on low resolution by doing our peak matching and centroiding based on this known line shape to give us high mass accuracy. Um, so that's an important thing to remember. Uh, if I simply right click on that accurate mass value labeled on the monoisotopic peak, you'll see this fairly long menu pop up. Some of them are scaling operations. Some of them have to do with calling out other routines. For example, I can call the NIST library search from here if I want to search that entire spectrum against the NIST library. But what we're going to do here is we're going to do our accurate mass formula ID, very much like we would do on an accurate mass instrument. It's really, in fact, the menus and dialogues look very similar if you've ever used the high resolution instrument to do accurate mass. And we call our method of formula ID, we call it CLIPS. That's our acronym, which stands for Calibrated Line Shape Isotope Profile Search. And we'll see why we call that in a second. So we're going to choose the clip. So that's in general, you're going to go in, you're going to click on the ion of interest, you're going to go and right click it, you're going to choose the clip search menu, and it's going to pop up this dialog. And what does this dialog look like? It looks like you're going to be doing an accurate mass search. So the things that are important is, of course, you want to choose your elements, and obviously the more elements, the more, if you don't know anything about your unknown and you have to open this up, you're going to get a lot of matches within a given mass error window. Because even on an accurate mass instrument, let's say the instrument is good. You know the instrument is good to 5, maybe to 10 ppm. You have to set a window to look for formulas within that accurate mass window. And it very rarely will produce a single formula. It will typically produce a list of formulas. I like to work in millidaltons. In this sample, this is a very clean sample. One of the things that you have to be careful of is that you don't want to set too narrow a mass tolerance window. If you have noisy spectra, it's going to reduce the mass accuracy. And if you have too narrow a mass tolerance window, you're going to miss the formula. Uh, Now, so the question is, what do I choose? Well, the specification for the instrument says 5 milldalton, but that's for a ideal sample. It's a test sample that you have a very clean spectrum, you have very high signal to noise, you have a very strong molecular ion, and certainly 10 milldaltons for this sample is fine. But in the real world, that's you're going to not see as good a mass accuracy. So what I general rule of thumb, you use between 20 and 30 milldaltons for a real world sample for the mass accuracy window. And then, of course, you hopefully know something about the chemistry and of the sample. So you would choose your element table. If you look at it and you say, oh well, it's sulfur containing or something else, you would just simply add those to the list. And what it will do automatically when this analysis mode says dynamic, what it does is based upon the mass of the compound that we're looking at, it'll choose based on some chemistry rules, a range of elements to use for trying to calculate all the potential formulas within that mass range. Okay. Um, we're going to get to this a little bit later. What this means, let me delete that right now. About that. So we're going to be searching this. We know there's fluorine in this, so we've added fluorine. Uh, there's no oxygen in this sample, but I'll leave that in there just to show you how it works. There might be a nitrogen, I forget, that's in the sample. And then, of course, the hydrogen, carbons, again, these ranges are pretty open. So what do? We tell it to search. So what it's going to do, it's going to find all formula that fit within this mass window. And it's going to give us a list of those formula. Let's do the search and see what happens. So it's done the search, and you get a fairly long list here, okay, of potential compounds. If you had a TOF instrument, this list would be much shorter because you have better mass accuracy on a TOF instrument. So what can we do to compensate for that? Oops. Search. It's weird. Got something set up wrong here. Oh, okay. Yeah, of course. The defaults, you can, if you get lost or whatever, you can say reset to the defaults and it resets to the basic instrument defaults here. And then you can go back and say we have carbon, we have hydrogen, we have maybe we have nitrogen. We don't know. It's an unknown. We have oxygen, and we suspect it might have fluorine in it. But let's say we didn't know it had fluorine in it, and we only thought it had CHN and O. And so we would do a search, and we would get some values. And this is the list of formula candidates within that 10 milldalton window. And if you had a high resolution instrument, this list would be a bit shorter. So which is the right answer? Well, you'll see that there's this additional column, which I'm sorting by default, which is called spectral accuracy. And you'll see that it goes from, in this list, it goes from 90 to 98.7, which isn't bad, okay? If you look at the last match on the list, and this is the mass error, and you're really, just because the mass error is smaller, doesn't mean that that particular compound is a more likely candidate. Statistically, you have to consider all of the formula within that mass window to be candidates, okay, provided that you shows that properly. But the mass accuracy, what it's done is it's calculated from the isotope profile. So if you go down here and we look at 90, the mass accuracy, you can see we sorted these formula by mass accuracy. You can see that there's what it's showing here is this black line here is the calculated isotope profile for that formula. And it's overlaying it to the calibrated data, which is the red there. And obviously, it doesn't fit very well. And basically, this is A plus 2, or excuse me, A plus 1 here is way off. And thinking like a chemist, you say, well, the carbon count's way off. All right. And so that's obviously not the right answer. And that's reflected in the spectral accuracy value of 90. Now, as I move up the list, what you'll see is the isotope pattern gets closer and closer. Zoom in on that a little bit so you can see that a little bit better. Move these panes like that, if you like. And, it fits. It's 98%. What that means is that 98% of this calibrated mass spectra is explained. The area fit underneath those curves is explained by this particular formula. And if I go to the best match, it's pretty good, 98.7. Again, there's very high signal to noise. Excuse me. So you can see that that match is pretty good, but it's not perfect. So why isn't it perfect? Well, it's not perfect because we don't have the right elements to take it into consideration. So now if we go and add our fluorine, this has, but let's do the search now. Now, and again, this is not a real world sample. This is perfect, but it's just here to illustrate a point. First of all, since I added fluorine, there's a lot more formula candidates. Okay, you expect that. The more elements you add, the more candidates you get. So again, we have our spectral accuracy match. And if you look at the matches, again, down here at 98%, you can see the error in A plus 1 and A plus 2. As I move up the list, see that the isotope profile gets better and better until I get to the top here where it's really good. It's like almost a perfect match between the calculated theoretical spectrum and the mature spectrum. Of course, 99.73% is really good. You're not going to typically always see this in real life because we have interferences, we have background, we have noise, but you will typically always see the best hits bubble up to the top, at least around the top 5 in spectral accuracy. So now we've eliminated all these other formula candidates based on this additional metric called spectral accuracy. That's the power of what we do. So effectively, by combining spectral accuracy and mass accuracy, you're getting a much higher effective mass accuracy, which is the ability to discriminate the correct formula. All right, makes sense? Okay, so that's great. So let's say now that this is GCMS, so obviously we're doing electron impact ionization. We actually get a fragment pattern. You're trying to you don't know what the unknown is. It doesn't search well in the NIST, or maybe it searches in the NIST, but it's not definitive. And you want to confirm what some of these fragments might be. And again, I don't know if you know it, but the NIST search program has a built-in little application that can actually predict what these fragment formulas are, which is actually quite useful for real unknowns to validate that. So let's go and look at another fragment here. So we'll go and look at this fragment. So we know that we've identified the compound as OFN it is C10F8. So all these fragments should be daughters of that C10F8. So they should have less than 10 carbons and less than 8 fluorines. And let's go look at do the clip search again. Again, this is our element list. We could actually zero or eliminate these other elements because we know they're not there, but that's okay. We'll just leave them there. Again, we'll do the search. And again, we have C9F7. So that means we have a loss of CF. Okay, so this is a fragment of the molecular ion, and the loss was CF. And you can continue to go do that to help you understand what the fragment formulas are. That gives you lots of nice clues to working back towards the unknown compound and structure. Okay, and this is exactly what you would do on a high resolution instrument, except you might not have a high resolution instrument or it's on your wish list. If you had a high resolution instrument, you're always going to do better because you have better signal to noise because the TOF instruments, for example, are more sensitive, and you would have better resolution, which means that it's less susceptible to underlying interferences. And if you get really complex matrices, the weakness of lower resolution is that you can't see the underlying interferences. You can't resolve them spectroscopically. But for reasonably clean, well-separated peaks, you can do a bang-up job using our approach with a single quad, and you'll get comparable results to a TOF for those samples that you have a good enough sensitivity and you have a clean enough sample. Interestingly enough, you can actually also do some clever things like I can do a search here on the molecular ion. And what I can do is I can actually propose, if I propose what these fragments might be, I can actually tell the software to actually fit not just that molecular ion or just that fragment ion, but a whole series of ions and see how well it models to the fragment pattern. And what I have here is I can save parameter sets, which basically parameter sets include all the elements that you're going to use. So if you're always searching for certain types of compounds and you know they maybe only contain CHNO, you might save some element lists that contain just those compounds. And you can also save them. Here I have one for OFN I saved. And so here I have my element list that's saved. It saved the mass tolerance. What we have here, these are some chemistry rules, okay? You can set double bond equivalent range. You can set empirical chemical rules. So all that does is it filters out formula that don't make chemical sense. And you can go in and look at those parameters. They're based upon common chemical rules of that you can choose to set off or on. These are well-known and published rules. The other thing you can do is you can set the range that you're going to fit the mass spectral profile to, the ion profile to. So what I've told the software here to do is, okay, I'm going to search, this is my element search tables, but in addition, I want to take into account the loss of CF, loss of fluorine, loss of CF2, the loss of carbon, and the loss of CF3. Those are all common fragments for this particular compound. And instead of just looking at a narrow range of the single isotope, I'm going to actually look at all of the ions across that range. So I'm going to start at about minus 80 from the monoisotopic peak here, all the way up to 3.5 Daltons, which includes the A+1, A+2, and A+3 isotope patterns. So if I do a search here, what you see here is I've actually fit and explained every fragment ion here based upon that search. And you can see the fitting, the overlay of the black and the red is very good. The spectral accuracy is very good. And what's interesting is it'll also tell you what the relative concentration of the fragment ions are that make up this compound. So because it had to actually go and fit all those fragments and figure out best optimum fit. So it's pretty powerful. That's kind of a more interesting academic case. In general, you're going to go in, you're going to have your unknown, you're going to try to identify the molecular ion if possible, and then you're probably going to go and look at some fragment ions. Let's go look at a more real life sample, but still a pretty clean sample. By the way, it does remember your most recent files that you open. So if you go open up a file in the past, it will remember what you opened up. So remember, I opened up a pesticide file. That's my OFM. This is a file of volatile organic compounds that's used for an environmental work. So let's just open that guy up. See, it says it already found a calibration and it's going to be used. If it didn't find the calibration, it would automatically create it. Um, this is the VOC run. Nice, pretty nice clean run. You can see at the end of the run, the calibration gas was turned on. So that's what it's using. So this is now calibrated data to accurate mass and accurate spectral accuracy. That's one of the compounds that I'm interested in looking at. Um, let's zoom in on this ion here. Now, this is a very common issue that happens with EI fragmentation, which can be problematic when you're doing accurate mass measurements, uh, even on high resolution, although it doesn't really affect it that much, is that we get the molecular ion here. Okay, so you can see the molecular ion here. But what's this peak on Dalton before? Very commonly, what you see in EI fragmentation is you'll see an ion, and then you'll strip off a proton, and you'll see the loss of a hydrogen. And the problem here is obviously that has an isotope pattern that goes like that. It will actually interfere with the molecular ion, or if this can obviously happen with fragment ions here. So how do we take care of that? We can still do accurate mass. We can still get a good idea of the mass, but how do we actually fit this isotope profile to get spectral accuracy? Well, the beauty is that since we know what these line shapes are, we can tell the software, since the only fragment that's going to be close to the molecular ion is going to be minus a hydrogen or maybe minus two hydrogens, we can tell the software to take that into account. So how do we do that? So we go into our clip search, and what I recommend, and I'm going to take this away first. Let's go and do our formula search. Notice I opened up the mass window about 30 milladaltons. That's generally what I like to use on real samples. CHNO is my element list. I do a search. I get my element list, and I got 14 candidates based upon the mass accuracy of window of 30 milladaltons at relatively low, low molecular weight, 106 here. Spectral accuracy, if you look at the overlay, it's not very good. And it's not a good metric to help me determine which of all these formula is the right one. They all look kind of crappy, right? Why is that? The reason for that is that because we have a fragment interference with the molecular ion and the molecular ion minus, a proton here. And actually, I can see it here. This is actually minus two protons and even three protons. That's what's going on there. So, but we know that's common. We can simply tell the software to take that into account. So when I do the search, you see this ion series choice here. What you do is you say, I want to, and it actually remembers common relative. Commonly, you can add to this list if you like. But I know that you also want to take into account the loss of a proton, very common in GCMS, and I'm going to look for the loss of either one or two protons. So I suggest that when you do your work for unknown analysis for GCMS, you should always add a repeat unit in. And again, you can save this in the parameter sets here. Always take into account the loss of a proton or two protons. That way, if you do have this kind of interference, it's automatically handled for you. doesn't really hurt it, even if it's not there. If it's not there, it doesn't really penalize you. So you should always use that setting. Okay? So you say, let's do the search, see what happens. So now, lo and behold, the spectral accuracy for the compound here, which is C8H10, is the best spectral accuracy is 99.48. And you can see now that the isotope pattern, and I told it to match the pattern from -1 m over z to 3.5, and you can see where the black ends about there. Now it's taking into account the interference, and in fact it knows how much of the deprotonated species is there. That's your mixture results there. It's about minus a proton is about 17% actual molecular ion as well. So that's very important for GC MS applications. The other thing that you can do here is if you want to just validate that, you say, okay, well, I got the formula. And that's what mass spec accurate mass can do for me. It gives you the formula. It doesn't give you the compound. It doesn't give you the structure. Mass spec can't do that unless you start trying to work back from fragmentation patterns and doing MSMS, so on and so forth. But I can go and do a library search against the NIST library. So if you have the NIST library and the NIST software application installed, I can simply click on the spectrum box here. I can do a library search. And this is the NIST search results that it just calculated. So there's my MassWorks. This is the NIST search result window. This is the matches. So what it found here is a very high quality match of the NIST library, match value of 972. Again, the formula for this is C8H10. Okay, C8H10 agrees. That's a nice validation. Now, the nice thing is with looking at fragmentation patterns through the NIST search, if it's in the library, is you'll notice that the top matches are all have the same formula. Well, accurate mass can't discriminate between those compounds because it only gives you the formula. But what the NIST search is doing is actually using that fragmentation pattern as a fingerprint, okay, to help us discern the correct compound. So they work together quite nicely. Let's see. The other thing that you can do is, of course, you get a formula here. You say, well, gosh, what is that? Is that something that's real, or is that something that maybe doesn't really exist in the world? I can right click on that guy and I can tell it to go to a ChemSpider database, do a search, that formula against the ChemSpider database. And lo and behold, sure, there's lots of compounds, as you would expect for this, that are in the database. So that, another way to confirm that indeed you're on the right track to an unknown compound identification. So those are some of the tools that we have to help you and assist you for doing unknown formula ID. Obviously, first and foremost is the ability to do formula identification through the combination of mass accuracy and spectral accuracy, which gives you a very high effective mass accuracy. The limitations here are the samples have to be relatively good signal to noise. They have to be relatively free from background interferences, although there's ways to take those into account, which I can show you, but I'm kind of going over my hour limit here. So why don't we kind of stop here, and hopefully this was a pretty good overview so far. I can continue going. I can answer your questions, and let's